right, can you hear me? It's good? Yes. So nice to see so many faces. Welcome to my talk, Electrifying Norway with F# and domain-driven design. So I already had an introduction, but just briefly, my name is Almir Mesic. I work for a company called Ren. It's a Norwegian company located in Bergen. I'll get back to what Ren does in the next slide. I started off with C#, but in 2019, I discovered F# and been doing F# ever since. So, what does Ren do? Together with Norwegian grid companies, we develop guidelines and tools being software, to ensure best practices in the design, installation, operation, and maintenance of the electrical grid. The software me and my team work on, it's called Netlin. And Netlin is a design and simulation software for overhead power lines. It lets you plan line routes and simulate loads. So that being the mechanical load, the weight of the system itself, as well as climatic loads. So we do wind, ice, snow, and even the combination of all of them together. We use a finite element method engine, and it's powered by a company called Focus. And for those who are not familiar with the term, finite element method is a mathematical technique used to predict how objects behave under various physical conditions, such as stress, heat, or vibration. So the main objective of our software is to help the user design safe and secure overhead power lines. Because, you don't want your overhead power lines to collapse during strong climatic conditions, such as, snowy or windy conditions, like we have in Norway. So that's the one objective. The other objective is to also make the overhead power lines cost efficient as well. So just to show you the software itself, it's a desktop application. You create a project, you get the map of, this is Norway. You zoom in, you place out, in this case I've placed out 2 poles. And now we have the side terrain. So this is the terrain. These are pole 1, 2, and 3. They are 10 meters in height and 23 centimeters in circumference. The red line, that's the power line. So once you've mapped out or placed out your poles, the next thing is then to analyze. So you take this model, you push it into the finite element engine, and then you run a certain set of loads. So in this case, we have minimum temperature, maximum temperature, wind, ice, skewed ice, and so on and so forth. So you hit analyze, you get back a result, and based on that result, you get an indication of how much, for instance, how much sag there is on your power line. And you also get an indication of like how skewed are the powers, or the poles. Like, will it collapse, will it tilt or not? So the percentage you see here, that's the capacity of the poles. So just to showcase an extreme example, this is a photo taken at Lønahorget at Voss, 1961. So what you see here is ice being frosted around the power line. So the wire, which normally had the circumference of 1 centimeter, had grown into 1.5 meter cylinder of ice. So you can just imagine how much more weight there is on the system. And if you take this even further, right? Like, let's imagine like one of the main power lines gets cut to a city during wintertime, and the conditions in Norway in certain areas are very hard, right? So, losing power during winter, and the only heat source you have is electric. It's quite a dramatic situation. So that's the context. Let me take you to the technical part. So Netlin is a desktop application. It's built on Windows Presentation Foundation. It started off with C#. It's still mainly C#, but yeah, we're trying to rewrite it. So we started off by creating a top-level project we call domain v2. And we did so last year in January, January 15th. And we are currently at 19% F# code and 80% C#. So Netlin is a desktop application, but we're slowly moving away to make it a web application. Right. So the question is, why did we go for F#? So to name a couple of things, immutability, of course, monadic error handling, so also known as railway-oriented programming, pure functions, or let's say functional architectural style. We try to keep the core, the main, as pure as possible, and then have an impure layer, meaning reading or writing from the database and the graphical interface. The absence of null is really nice. Algebraic data types, partial application, computation expressions, composition, and units of measure. The code we write is highly influenced by this book. Have you seen this book? Is this known, familiar? Right, good. So what we try to do is we try to model everything we do with algebraic data types. So we try to be as explicit as possible. Like we try to avoid to use float and double because it's not contextual of any domain, right? Like when you say double, it doesn't tell you anything. So in tandem of modeling everything using algebraic data types, we try to make illegal states unrepresentable. So hopefully if you do this part correct, then this should be true as well. Not always, but you could, aim for that at least. The third thing is ubiquitous language. So we try to use, or our code should reflect the language which is used in the domain. So in our case, we have staywire, pole, insulators, and so on and so forth. So that's the technical part, but our software itself is built primarily on this book. So NEC 445 is a European standard on how you should model overhead power lines above 1 kilovolt. So that's high voltage. And then we have this user guide. It says something about clearance control. So when you place out your pole, you need to ensure that it's not too near of a building, for instance. So that's all the context behind this. Let me showcase you code samples. And everything I'll be showing here is more or less directly from our source code. So units of measure. What if the compiler could understand units? So with units of measure, you can work with units at compile time. So let's start with the most basic, right? We have a floating number 42. And by using this notation, we can add a unit. So in this case, it's 42 centimeters. Let's create a function which converts centimeters to meter. And let's say you try to pass in just the floating number to that function, it won't compile. Equally, if you do it again with just the wrong unit, it won't compile. And then if you pass in the correct one, then you'll get the expected result. So that's the most basic example. The way we use it in our codes, this is directly from our code, is that we try to restrict as much as possible. So when we talk about length, millimeters in this case, we usually work with positive, right? Like we want to constrain it to what's actually realistic in the real world. So this is a single case union type. And then we use private because we want to ensure that the only way to create this type is to use a function. So for this, we check for if it's below 0, we return an error, or otherwise it's okay. We have a method to to extract the inner value. We overload the plus operator. Yes, so to summarize, we use type alias here. We strongly type positive millimeter. We compose with the existing type. We overload the operator. We have a constructor function. And then we use result for error handling. Extract, and then also case unwrapping. So this is a a way to extract the inner value of this type. So when you do this, you get this value out. And that's why you can do this, the plus sign. So in which context do we use this? So when we talk about diameter, we're quite interested in the top diameter and the bottom diameter of a pole. So one way to express this would be just say, okay, top diameter is a double, but that's not ideal, right? Because any double goes positive or negative, there's no unit, so there's zero type safety. Okay, let's add a unit. Okay, it's limited to unit, that's good, but still any millimeter goes, and so on and so forth. It's still not ideal, but the most ideal, in our case, is to be as explicit as possible. So in this case, we are limited to a millimeter as a unit. Unit must be positive, and it's limited to top diameter. So this is what we consider strong type safety. So the question is, when do we use top diameter? Like, one thing is to have it as a concept, but in which context do we use it? So when we calculate the wind load in our system, either being on the, like we do it both on the power line and the pole, we need to know the top diameter of the pole in order to apply the wind load on the system. So the way we do it is, again, single case unit type. We have a function called create top load. We take in 4 arguments. Return time, that's the frequency of the load. Elevation, how high is the pole above sea level. The top diameter, and the wind speed. And let's imagine for a second, this is the type signature. That's not ideal, right? That would be, arguments can get easily misplaced, any double of any range, and function signature is vague. So the way our code looks like, it's like this. We have a return time, it's its own thing, elevation its own thing, top diameter, wind value, and then wind load. So yeah, arguments cannot get misplaced, they are strongly typed, and function signature is precise and easy to contextualize. So let's look at algebraic data types, a bit bigger example. So let's imagine you have 2 poles with stay wire support on each end. You have a line. Our first categorization in our context is we differentiate between high voltage and low voltage. So high voltage, that's what you see outside urban areas. So that's 12 kilovolts, 24, 52, 66, and 132. Low voltage, that's the power you see in your house, so the power outlet. And we differentiate between, because I presume you all seen poles, like it's usually not just one line. It's not usually just the power line. You usually have multiple lines going. So we differentiate between a power line and then a utility line. So it could be ground or it could be telecommunications, so internet or and that kind of things. So for this, we use discriminated union. So here's with no value, and here we have with a value. Yes, so going next to the next concept, or at least in our domain. So these disks, this is called an insulator. And in our context, we have, they can either be glass, composite, or porcelain. And when we calculate the length of an insulator, we need to calculate what we call a material factor. So in order to do that, we need 2 arguments. It's high voltage and insulator material. We do pattern match. If it's, for instance, glass of 100 or glass of 66 kilovolts, we know the factor should be 5. So the way this is used is you pass in the length, you pass in the factor, you multiply the factor by the length, we convert it to millimeter, and then we get the insulator length. Yeah, just to mention piping, I guess this is familiar for you guys, but yeah, this is similar to what you have in Unix. So let's imagine you create a new DU case, discriminated union case. What will happen by default in F#? It will be a warning. Ideally, like I think it should be an error, but okay, we've turned on as an error. you'll get a warning stating that incomplete pattern matches on this expression. Yeah, steel has not been covered in this case. Okay, and I also want to show a small example of, like, as I mentioned, we are interested in the top diameter, and often we're interested in the bottom diameter, but quite often we are very interested in the diameter at the point where it touches the ground. So for this, we have a function. We calculate the gradient, and based on a gradient, we multiply by the height plus the bottom diameter. And now we know what the diameter is at this point. So the reason I'm just showing this as an example is how you can, by using strongly types and case unwrapping, you're guaranteed that you cannot pass in the wrong value in here. Okay, what you're seeing here is a specification taken from the standard I was talking about, the NEC 445 standard. So what this says is how skewed ice across should be applied to your system. So in this case, what you're supposed to do is, so imagine we have 2 poles with stay wire support, 3 lines going, is that you should apply 70% of your load on the 2 first lines and 30 on the last line. And equally, you should do the same thing on the other side. So the way we implement this is that we have a function alias stating that we take in a line and we get back a factor. So calculating the left one is, if it's first or second, it's 0.7. If it's third, it's 0.3. And the same thing we do for the right-hand side. Does this make sense? Yeah, and here in this case, I use a kind of different notation. This is the Lambda notation, but you could have just added a argument up here, but this is the same thing. Okay, right. Just want to showcase this as well. So equivalent diameter. So the reason why I'm showing this particular example is, I think this was 2 weeks ago, 3 weeks ago. Yeah, I sat down with our domain expert. He's the one who actually knows the specification inside out. And I showed him this code, and he could actually reason. And he's a non-technical person. So, and the fact that you can use the double quotation and you can write the formula in the way you want, using pi symbol or squared, it makes it very easy to read for the domain experts. Okay, so this went a little bit faster than I was thinking, but yeah, we'll have questions if people have questions afterwards. So, as I mentioned in the initial slide, talking about monadic error handling, what if you could handle errors at compile time? With monadic error handling, you can manage errors in a type-safe and composable way at compile time. So in F#, that's represented with the result type, similar to many other functional languages. So it's either OK or error. So let's say you have a divide by function taking A and B. If the divisor is B, sorry, if the divisor is 0, then it's an error. Otherwise, it's OK. So let's imagine you want to call this function 3 times. What will end up happening is you get this pyramid of doom code. And the nice thing about using railway-oriented programming or monadic error handling is that this particular pattern is abstracted by using the bind function. Or also a nice feature I really like in C#, in F#, is computation expression. So instead of piping and calling the higher order function, you can just use you open a computation, you call the exclamation mark, which we call the bang operator, which implicitly calls the bind function. So it makes it yeah, it depends on the eyes that sees this code, but I think it's quite legible. It's easy to read. Yes, so let's look at an example where we use the result type. So in this case, we have a tower, a sequence of towers. We map over it, and we produce a result. We create certain types, and for this, we need to evaluate the computation. So we get the tower category, the index, and the tower placement. And as you can tell, based on this code, we get the sequence in, and we get a sequence of result back. But that's not what we want, right? Like, we want a single result containing a sequence of tower placements, like this. So for this, we use a sequence result M. So for anyone who's familiar with FS Toolkit in F#, that's a really nice library I highly recommend. And in some cases, instead of just getting a single error, like you fail on the first, you maybe want to get all the potential errors that occurs in your code. You use the applicative function. Okay, now I'm going to just showcase a bit more complex. It's a fairly small code snippet, but the nice thing about this code snippet, it just showcases all the power F# has with just this terse code, but very readable. So when you place out, when a user places out the poll, he also places out the stay wires. So the whole point of a stay wire is to compensate for the incoming load. And quite often, the angle of the stay wire is not placed in the most optimal way. So what we do, we have a function which takes the entire system, it strips away all the stay wire support and makes the polls in steel, analyze once, and get back an indication of at what angle is the force coming from. And you end up with a result looking like this. So you get the most optimal angle. So in this case, it's usually between these like in the middle of the angle of this side. So the way this code looks like is we pass in the entire model. In this case, it's a project. We look for steel as a material. We create a function which strips all the anchors, and we replace the existing material with steel. And then we partially apply that function to this. And then we use the copy and update function in F#. And then we apply the updated sequence of towers in the route of the project. So to summarize, copy and update, we use the result computation expression, we use piping, we compose two functions, we partially apply the compose function, and we use the bind with the bang operator here. So just to quickly mention TaskResult computation expression. Result is nice for error handling, but what about result in an async context? So TaskResult computation is the way to go, at least for us. So this is the specification, and let me just showcase a simple example. So imagine you have a function called check site content where you pass in the URL. Which the first thing you do something async, you get the content, and based on the content, you validate the response. Okay, so let's look at the function which gets the site content. That's a task, so task computation expression, doing something async. We use the bang operator. And then we have a result-based function, which is being called in this case. So I love the fact that you can actually run two different effects in the same context. For this, for me, was really mind-blowing when I first learned this, but yeah, it's really nice. It's a really nice way to abstract the accidental complexity of your code. So the way we use it in our context is actually when we run the analysis. So we instantiate the HTTP client, we post our model, we analyze the model, and then we write the result we get back. And as you see, we wrap this in try with because we don't want to use exceptions. We only want to use strongly typed errors. So, yeah. Okay, I think this is my last content or last slide. I'm going to mention a bit about partial application. So, I don't know about you, but quite often the question I get when I say I do F# instead of C# is, how do you do dependency injection in FP or F# in this case? And there are obviously many ways to do it, right? But one approach is partial application. It's very straightforward. There's no magic. It's just purely just applying the dependency you want. So the way it looks like in our case is we first defined a function alias where you pass in the ID, project ID, and then you get back a cancelable task result of the view. So what we do is we say that we implement the dependency or the function. And for this, so this function here has another dependency, right? It's the iDocumentStore. So what we end up having here is iDocumentStore returning a get project. And that's not what we want, right? Like we want to resolve the function in such a way that it only returns a get project. So the way to do this is to partially apply to get the document store, partially apply it to the get project, such that your function signature is get project. And the way it's used is like this, for instance. So similar to what we did here, passing in a dependency is you just pass in a dependency in this context here. So you have the ID. Based on ID, you create the type and then pass it into the function, which is the project ID, and then you get back a view and then turn it into a response. So to summarize, function alias, Lambda with the get project return type. We partially apply the dependency, and then we inject the dependency in our function. Okay, that went a little bit faster than I imagined, but are there any questions?
Yeah. Firstly, thank you. I think your project is very great example of you using units of measure, because you're doing a lot of physics, and it literally makes these formulas even more readable than on paper, because you see all of these types, and that's very good. Thank you. I just wanted to ask about, because you use Martin, and as I know it's C# library, how do you use strong IDs, no strong type IDs when you have I've seen that you have project ID, and you obviously use F# records and not C#. Is this library works well with that, or you have to write a lot of wrappers around it?
Sorry, which library?
About Martin, because I've noticed
right. That's a good question. That's my colleague should have been here, because he's the one done that part. So I unfortunately I can't answer that. But I've reviewed his code, and from what I've seen, it seems to be working fine actually. Mm-hmm. But you do have to do some JSON serializer settings.
Yeah, I tried to do the same, and I have some issues minor, and it's kind of work, but then with strong types for me it doesn't work. But maybe they changed, so that's what I was asking.
I see. Yeah. Mm-hmm. No, I think you have to do some JSON serializer settings, mm-hmm. which is not ideal, but yeah.
And it's a link your queries, not linkable, but compilation of queries to the SQL. It didn't work with strong types, I think, but okay. But thank you.
Thank you.
So I have a couple of questions. The first one is, how has this partial migration from C# to F# improved the quality of the product? What is the impact on the users? And the other question is, you mentioned you are transitioning towards a web application, and I wanted to ask you whether you are using Almir or some other front-end framework.
Yeah, so the first question was in what way has it impacted? So the first thing we notice is way fewer bugs. And the time to correct the bug is like, it's so much faster. Like our domain expert, he's shocked. Like he doesn't understand like how fast we can locate the error. And that's, yeah, so that's the first thing. It's correcting the bug goes much faster, and the amount of bugs are way less. And the second part you asked for Elm. So our front-end team, they are not function. they went for like the standard React. Yeah. So it's like we are on the back-end team and they're on the front-end, and we were like, okay, you can just choose whatever you prefer. And then we have an open API specification, and then they consume our contract.
Okay.
Yeah.
Yes, sir, another question. I had an issue with F# with computation expressions like async or task, that if there are exceptions, their stack trace would be very, very wrong. And because of that, like, it's very hard to debug code compared to C#. Like, do you have the C# because you always use try catch and results you don't? Because I'm just like kind of addicted to stack traces because like they help me a lot like to debug. And you're saying that it's easier it became, but for me like it became in some ways harder to find errors in F#. So like, what did?
Yeah, no, I understand. That's a good question, because in some cases you are interested in getting the entire stack trace. Like what led, like how did you come to that point, right, of error? But yeah, we haven't experienced, like we just strongly type our errors, and we haven't thus far experienced like that we miss exceptions, but the stack trace. So I don't know, maybe you could combine the exception inside the error, like I don't know what people prefer.
No, there is the issue with computation expressions that they fundamentally work very wrongly with stack traces. Like there is like even issue like on F# like as a language about that, but as I know, it's still not fixed.
Okay.
Yeah.
So near the start of your talk, you had a data type representing positive quantities in millimeters, right? Now, you defined a version of the plus operator so that would work. Now, subtraction obviously is not always going to work, and for like standard programming with division, we just kind of pretend that you never divide by 0. But I'm wondering if because you need to be thorough and precise in your domain, whether you're, how you handle things like subtraction. Are you like explicitly propagating an option through everything? Are you just pretending that's not going to happen? Or have you come up with some other way to describe?
I'm not sure I understand your question. So you said like subtraction won't work in certain cases, or?
Yeah. So if I have two positive quantities and I want to take the difference of them, right? I return like either I get a positive number or I've gone outside of the domain. Like
yeah, right.
So
yeah,
are you saying like, would you have you had this problem and have you dealt with it by saying I'm going to return an option, or are you saying I'm going to return a possibly negative, like a
I see. Yeah. No, what we usually
quantity.
do, like in that particular case, if I remember correctly, you call the since it might produce an error, we just call the create function back again. So you subtract one number by the other, and then you call create again to ensure that it is a positive number you produce. So in the end, you will end up having you produce an effect.
Right, and that's the responsibility of the person writing the domain code to perform that computation.
Yeah, and in some cases, like you're not interested in actually failing the computation. So what we do is like, I've seen code we have so option from result, and then we're like, okay, it's an option, it's fair enough. Like we want to deal with it explicitly. So, but usually we just call the constructor and then go back to the loop and treat it as an effect.
Yep. Okay, and you've not found that unorganized.
No, I mean you could say like maybe it's too strict, but I'm in the camp of like it's better to be too strict than the contrary.
Yeah, agreed. Cool. Thank you.
Thank you.
So I have two questions.
Yep.
One is I'm not quite clear whether you are implementing new functionality in F# or taking existing C# code and migrating it to F#.
It's both. Both. So we are both replacing parts of the C# code because there were so many bugs. But in tandem, we're developing this. I mentioned the book, right, of high voltage power lines. That's purely written in F#. So because we have to take care of the legacy application being low voltage, but the high voltage is purely F#. But parts of the old code is rewritten in F#.
So the other question was, you talked about getting fewer bugs and fixing them more quickly, which sounds great. But I wonder whether you can quantify that. In particular, there is a cost as well, right? You write quite a lot of code whose only purpose is to put on and take off units of measure. Can you compare those two? Is there, are you doubling productivity or getting 20% or what?
Oh, that's a good question. So, are you asking me if I do have actually some data to back up or?
Well, ideally, yes. Do you have some data and?
No, this is more I would say a subjective thing. I feel like that we're sorry, I don't have any data to support my claim. It's more based on the experience of working on.
So if you were to hold your finger in the air and just feel which way the wind is blowing, how big a gain do you think you're making?
40-50% maybe. Yeah.
Any other questions? Oh. Yeah.
A lot of great questions, by the way. That's really nice.
Hey, maybe I can add to this very question is that, for example, we didn't use units of measure because we had F# and C# interop. And then when I did refactor to complete F#, there was 30,000 lines of code that would be affected by this change. And I decided it's not worth it because we wouldn't benefit from it. But I think we don't really use physics. For me, it would be I have either ID of employee or ID of skill or ID of activity, and those IDs would mesh up. And for me, it just wouldn't work. And we didn't have any bug in just meshing those in 10 years. So in our case, wouldn't be. But I wanted to ask, I think I have 3 questions that could be relevant to outer public. One question is about testing, because you said you were migrating some legacy application. So how well it was tested and what kind of confidence did you get from your migration?
So what we typically did is we first wrote the test for the existing C# code, then we just swapped out with F# code.
Okay. Then the second one would be how much interop is still in place, because I can tell that using types that are just wrapped in single case discriminated union, using that from C# is not always just very nice. I mean, you have to write, there's a new type and stuff like that.
Yeah.
And I actually decided that I don't really want to use that. And also, if you have it serialized in JSON, for example, you have C# class, when one type or one field is discriminated union, then you have to write it as a field and case and stuff like that. So does that happen for you or not?
One particular case I've noticed, which is not well supported, is partially applied functions. They don't resolve it at all in C#. So you just have to type out you have to create the function again manually. So but our experience is it works 90% of the time, and there's some quirks, but it's sufficient for our case.
Okay, and maybe the final one, you were showing some HTTP call. And for example, we had an example when we created a F# record that was passed through minimal API in .NET, but we included option in that record, and it didn't work. So we had to we had to go for nullable, I think, So if you have any experience with that.
Well, as a general rule, following the domain modeling made functional book, when you're at the edges where you do I/O, either being HTTP calls or database, we strip all the strong types away. So at the edge, it's just purely simple POCO types using null or whatever. And then once you've come into our domain, then it's strongly typed and protected. So at the edges, it's anything can happen. I don't trust the outer world. Just give me what you have and let's see what happens.
We have it in similar way,
Yeah.
Okay. Thank you.
Thank you.